CIET NCERT presents audio book Ganit Manjari Part 1, Textbook of Mathematics for Grade 9.
Chapter number 6, Measuring Space, Perimeter and Area. Page number 118. On the top right corner, we are provided with a QR code, scanning which you can reach out to the additional resources to this chapter. We are provided with a figure here, figure 6.1, athletes at the start of 4 into 100 meters relay race. In figure 6.1, athletes at the start of 4 into 100 meters relay race are given here. In figure 6.1, you observe athletes assembled at the start of a 4 into 100 meters relay race. The tracks are laid out and the athletes are all set to go racing down the tracks. Do you notice that the athletes are not at the same starting line? Those in the outer lanes seem to be starting ahead of those in the inner lanes, while the finish line is the same for all of them. What could be the reason for this? The distance between the starting points of adjacent lanes is called the stagger. Notice that the stagger continues all the way to the outermost lane. Do you think the stagger gives anyone, those in the outer lanes or in the inner lanes, an unfair advantage? Why or why not? On that basis, can the organizers work out the length of the stagger between lanes? Think and reflect. In my school, the playground is too small to have a 400 meters track. So, the school constructed a 200-meter track instead. Does this mean that we need a smaller stagger for the race tracks in my school? That is, smaller than the stagger used in the Olympics for the same 4 into 100 meters relay race. To answer the question about the lane staggers required on a 4 into 100 meters athletics track, we need to know how to find the length around a circle. Page number 119. 6.1. Perimeter of a shape. Given any shape, its perimeter is the total length around its border. Imagine a tiny insect going for a walk around its border, never turning around till it returns to its starting point. The perimeter of the shape is the total distance it travels. So, a square with side A units has perimeter 4 into A units. An equilateral triangle with side A units has perimeter 3 into A units. We are provided with two pictures here, figure 6.2a, in which we find a square of side A units, and figure 6.2b, in which we have a triangle with side A units. The perimeter of a rectangle with length A units and width B units is 2 into A plus B units. Note that the formula for the perimeter of a square is a special case of the formula for the perimeter of a rectangle with A is equal to B. Here, we observe a circle with radius r units. What is its perimeter? How do we find out? Here, we are provided with a figure 6.3, in which we find a circle with center and radius r marked on it. Think and reflect. What is the connection between this question and the one about the 400-meter athletics track? To answer the question about the perimeter of the circle, we must go step by step. What happens to the perimeter of a square if we double its side? It doubles too. The ratio of perimeter to the side is 4:1. This is so far all squares. As the side of the square gets larger or smaller, the ratio of the perimeter to side stays fixed at 4:1. We are provided a figure 6.4 in which we find ratio of perimeter to side is 4:1. We find two squares on the graph paper. In the first one, the side of square is 2 units with perimeter equal to 8 units. And in the besiding square, we have the side of the square as 4 units and perimeter to be 16 units. Page number 120. For equilateral triangles, the ratio of perimeter to the side is 3:1. As the side of the equilateral triangle gets larger or smaller, the ratio of perimeter to side stays fixed at 3:1. We have figure 6.5 in which we find three circles having different diameters and circle is marked with C. What about a circle? What is its perimeter? Usually called the circumference in terms of its diameter. Is the ratio of circumference C to diameter D the same for all circles of all sizes? As given in figure 6.5, what do you think? 6.2 Perimeter of a circle. The C/D ratio. In ancient days, people realized that the ratio of the circumference to the diameter of the circle does not change if we change the size of the circle. Let's call this ratio the C/D ratio of the circle. What is the value of the C/D ratio? How would you estimate this ratio? Home measurement. You can do a simple measurement at home to estimate the C/D ratio. Take a cotton reel with thin thread around it. Measure the diameter D of the reel as accurately as possible. Unwrap and then tightly wrap the thread around the reel 20 times. Unwrap it again. Measure its length L and calculate L upon 20D. This is the ratio we want. For accuracy, the thread should be very thin. Please do the experiment. Do you get a ratio between 3 and 4? Between 3.1 and 3.2? It is also possible to estimate the C/D ratio using pure geometry, that is, without any measurements at all. Can you imagine how? C/D's adventurous journey from ancient approximations to the exact formula of Madhava. Mathematicians have been fascinated by circles and the C/D ratio since ancient times and across geographical regions. Page number 121. This constant, which we now call pi, we say pi as in PIE and not as in pizza, represents a bridge between many different areas of mathematics and connects the straight-edged world of polygons with the infinite curves of nature. While early civilizations relied on practical, good enough values for construction and trade, the pursuit of this ratio eventually became an important pastime of mathematicians. that help to benchmark the sophistication of mathematical theories. In Mesopotamia, c. 1900 BCE, mathematicians moved beyond the crude integer value of 3. They realized that a circle had a perimeter. That was slightly larger than the hexagon inscribed within it. They concluded that pi should therefore be larger than 3, and they set the value of pi to be 3 plus 1 upon 8, that is equal to 3.125. Here we have a figure 6.6 in which the Mesopotamian hexagon to circle comparison is given. Can you see why this shows that pi is greater than 3? We have a circle in which hexagon is inscribed and the center of the circle is marked as O and the radius of the circle is r is equal to 1. By 250 BCE, Archimedes of Syracuse brought a new level of rigor to the problem. He trapped the value of pi between the perimeters of inscribed and circumscribed polygons. By using both an inscribed and circumscribed hexagons, Archimedes showed that pi is between 3 and 2 root 3, that is approximately equal to 3.46. Working his way up to 96-sided polygons, Archimedes found that 3 whole 10 upon 71 is less than pi, which is less than 3 whole 1 upon 7. Here we are provided with one more figure 6.7. Archimedes' method utilizing inscribed and circumscribed polygons. Can you notice why this diagram of an inscribed and circumscribed hexagon tells us that pi is between 3 and 2 root 3? Hint provided is use the Bodleian-Pythagoras theorem. In this figure, we find a circle with a hexagon circumscribed and a hexagon inscribed in the circle. Radius of the circle is r is equal to 1, and we also have a perpendicular and side of the hexagon is a units. Page number 122. In about 150 CE, Ptolemy of Alexandria refined Archimedes' computations for use in his astronomical tables, giving the ratio 377 upon 120, which is approximately equal to 3.14167 for pi. Shortly thereafter, in China, a circle cutting method of Liu Hui 263 CE laid the groundwork for two breakthroughs due to Zhu Chongzai 480 CE. Zhu pushed the polygon approximation method to 24,576 sides. He used this to discover the Euler approximate ratio of 22 upon 7, approximately equal to 3.1428 for pi, and also the mu close ratio of 355 upon 113, approximately equal to 3.1415929 for pi. The rational fraction 355 upon 113 is so close to pi that it remained the most accurate value for pi in the world for over 800 years. It is now known that no single rational fraction with denominator less than 15,000 can be as close to pi as this fraction. In 499 CE, Aryabhatta provided a value of 62,832 upon 20,000 approximately equal to 3.1416 for pi. Crucially, he described this value as asana, that is, approaching or approximate, a profound insight suggesting that the ratio could not be given exactly as one simple fraction. Meanwhile, Brahmagupta 628 CE suggested the use of the value square root 10 approximately equal to 3.1622 for pi. While slightly less accurate, he chose it for its mathematical elegance and the ease with which it could be manipulated in equations, a preference that saw square root 10 become the dominant approximation in the Arab world and medieval Europe for centuries after. Over the ensuing years, many great mathematicians studied pi, including its approximations, but no approximation was as accurate as Zoo's 355 upon 113, or as algebraically simple as 22 upon 7, 3.1416 and square root of 10, until the work of Madhva of Sangangrama, who changed the game forever. Madhva realized that pi was not just a number to be approximated by fractions and other finite algebraic expressions, but a limit to be reached. Madhva thereby discovered the first exact formula for pi. Pi upon 4 is equal to 1 minus 1 upon 3 plus 1 upon 5 minus 1 upon 7 plus so on. Is that not a beautiful formula? Madhva's formula, given in the form of an infinite series, was a tectonic shift for mathematics. By moving from the geometric cutting of circles to the analytical summing of numbers, Madhva birthed the area of mathematics known as calculus. Page number 123. His infinite series enabled him to calculate pi to 11 decimal places, 3.1415, 9265, 358, proving that the relationship between a circle's circumference and its diameter was a window into an entirely new area of mathematics. Better and better infinite series were developed over time that gave more and more digits of pi even more quickly. The key breakthroughs on the problem after Madhva were due to Neelkant c. 1500, Machin 1706, Ramanjam in 1914, and the Chodnovsky brothers 1988, who skillfully extended the ideas of Ramanjan. Today, using their algorithms, we now know pi to Niels hundreds of trillions of digits. We will learn more about the area of calculus in later grades. In 1706, the Welsh mathematician William Jones used the Greek symbol pi to denote the C upon D ratio because pi is the first letter of the Greek word perimetros for perimeter. The symbol was made popular by the Swiss-German mathematician Leonhard Euler, pronounced Euler. We continue to use the same symbol today. 6.3 pi is irrational. The digits of pi go on forever with no visible pattern. You already know that fractions give rise to decimal expansions with a rhythmic pattern. Example, 1 upon 3 is equal to 0.33333, so on. 1 upon 11 is equal to 0.09090909 and so on. 1 upon 7 is equal to 0.142857, 142857 and so on. But for pi, there is no such pattern. It turns out that pi cannot be written as a ratio of two integers. Such numbers are called irrational. Remember, a rational number is a number that can be written as a fraction a upon b, where a, b are integers with b not equal to 0. Example, numbers such as 1 whole 2 upon 3, minus 7 upon 11 and 1.4. In grade 8, you learned that square root 2 is an irrational number. From their writings, it seems that Aryabhatta and Zhu Chongzhi regarded pi as irrational. Centuries later, 1761, the mathematician Lambert showed that this is so. Pi is irrational, but to prove this requires more advanced mathematics, which we will learn much later. Page number 124. Since pi is irrational, there is no best fraction for pi. If there is any fraction that is close to pi, we can find another fraction that is closer. The well-known fraction 22 upon 7 is good enough for most practical uses. But it is important to note that pi is not equal to 22 upon 7. They are close but not equal. So we write pi is approximately equal to 22 by 7 and also pi is not equal to 22 upon 7. In the same way, we can write square root 2 is approximately equal to 1.414 and also square root 2 is not equal to 1.414. As noted earlier, a much better approximation for pi is 355 upon 113. We have a picture of fun fact here. We are provided with a picture in which we find two people on a scooter are observing a train with the value of pi marked on the wagons of the train as 3.14159265358973 and so on. The decimal places are endless. Fun fact. Here's a fun way to remember the first few digits of pi. How I wish I could recollect pi. Count the number of letters in each word. 3, 1, 4, 1, 5, 9, 2. And you get the digits of pi. So, pi is approximately equal to 3.141592 and so on. Since pi is approximately equal to 3.14 and also pi is approximately equal to 22 upon 7, March 14 written as 3-14 in North America is celebrated each year as Pi Day, and 22nd July written 22-7 in India is celebrated each year as Pi Approximation Day. Page number 125. 6.4 Length of an arc of a circle. The circumference of a circle of diameter d is pi d. Since the diameter is twice the radius, we can also write the circumference of a circle as 2 pi r, where r is the radius. What will be the length of a semicircle with the same radius r? As given in the figure 6.8. Here we are provided with figure 6.8 with two semicircles making a full circle. We find that a circle is there with center O and 2 points A and B across the diameter. OB is marked as R. The semicircle above is red in color and the semicircle below is blue in color. If we reflect the circle in the diameter AB, the red semicircle and the blue semicircle exchange places. This means that they have equal length, which is 2 pi r divided by 2 is equal to pi r. Instead of reflecting the figure in the diameter AB, we can also imagine rotating the whole figure around the center O through an angle of 180 degrees, that is, through a half turn. The effect is the same and we get the same formula for the length of the semicircular arc. What will be the length of a quarter circle with the same radius as given in figure 6.9? Imagine rotating the entire figure through 90 degrees, clockwise or anti-clockwise. Each quarter circle moves and covers another quarter circle. So each quarter circle has the same arc length and this is equal to 2 pi r divided by 4, that is equal to pi r upon 2. We are provided with figure 6.9 which explains 4 quarter circles make a full circle. We find a circle with diameters AC and BD intersecting at O. Note the following. The formula for the length of a semicircle may also be written as 2 pi r into 180 degrees upon 360 degrees. Page number 126. The formula for the length of a quarter circle may also be written as 2 pi r into 90 degrees upon 360 degrees. From these, we can guess the formula for the length of an arc of a circle in terms of the angle it makes. That is, the angle it subtends at the center of the circle. If the arc is AB and it subtends an angle theta degrees at the center O of the circle, the length of the arc is 2 pi r into theta degrees upon 360 degrees. We are provided with a figure 6.10 which explains the length of an arc of a circle. We have an arc AB marked which traces an angle AOB as theta degrees. A closer look at a 400 meters athletics track. Figure 6.11 schematic diagram of a 400 meters athletics track. In the figure, we find there is an athletic track of 400 meters and points A and B are marked inside the track. In figure 6.11, there is a schematic diagram of a 400 meters athletics track. Page number 127. Figure 6.11 depicts a 400 meters athletics track. You can observe two straight sections of length 84.39 meters each and two curved portions which are semicircles with a common center points A and B. The innermost semicircle on each side has radius 36.5 meters. The width of each lane is 1.22 meters. Let an athlete make one complete circuit of the track. What is the total distance she runs? Let us assume that she runs at a distance of 0.3 meters from the inner border. She runs two straight sections of length 84.39 meters each, a total of 168.78 meters. She also runs two semicircles of radius 36.5 plus 0.3 meters, that is 36.8 meters. The two semicircles together make up a complete circle. Its circumference is 2 into pi into 36.8, that is equal to 2 into 3.1416 into 36.8, that is equal to 231.22 meters. The total distance run by the athlete is therefore 168.78 plus 231.22, that is equal to 400 meters. Now consider two runners, one in the innermost lane, the other in the second lane. On the straight stretch, the two runners run the same distance, but on the curved portions, the runner in the second lane runs a greater distance because her semicircle has a larger radius. It is to compensate for this that staggers are needed. Think and reflect. What is the difference in radius between the first and second lanes? Use the figure 6.11 to find the stagger needed by the runner in the second lane. Will an equal stagger be needed between the third and second lanes? 6.5 Problems, Puzzles and Paradoxes on Perimeter. We close this section by looking at a sprinkling of interesting problems around the theme of perimeter. Example 1. Two circles of equal radius are located such that each circle passes through the center of the other circle, as given in figure 6.12. Given that the radius of each circle is r units, find the perimeter of the shape formed by the two circles in terms of r units. Ignore the dotted portions that lie within the circles. Page number 128. Here we have two congruent circles centered at A and B. Each one passes through the center of the other one. The circles intersect at C and D. We need to find the total length of the two red arcs given here in terms of the radius r unit. Consider the triangle with vertices A, B, C. Since AB is equal to R, AC is equal to R, BC is equal to R, the triangle is equilateral. Hence, angle CAB is equal to 60 degrees, that is equal to angle CBA. We have figure 6.12 here, in which we find two circles with centers A and B intersecting each other at C and D. These circles are congruent to each other as they have same radius. Similarly, angle BAD is equal to 60 degrees, that is equal to angle ABD. It follows that angle CAD is equal to 120 degrees, that is equal to angle CBD. Hence, each dotted arc is 1/3 of the circumference of the circle on which it lies. Hence, the total length of the two red arcs is 2 into 2/3 into 2 pi r, that is equal to 8/3 pi r. Example 2. In figure 6.13, we observe points P and Q and two paths connecting them. The first path is made up of the semicircle A. The other path is made up of three semicircles B, C and D. Which path is longer? Choose one. First part, path A is longer. Second part, path B plus C plus D is longer. Third part, the two paths have equal length. Try to answer this before reading on. In figure 6.13, the semicircles are represented here in different colors. one semicircle A is red in color, and we have the other parts of semicircle B, C and D represented in blue color. Let us solve the problem using algebra. Let the radii of the semicircles A, B, C, D be denoted by A dash, B dash, C dash and D dash. Then the length of semicircle A is half of 2 pi into A dash, that is equal to pi A dash. Similarly, the lengths of the semicircle B, C and D are pi B dash, pi C dash and pi D dash. So, the length of the second path is, taking pi common, within brackets B dash plus C dash plus D dash, and that of the first path is pi A dash. Which is bigger, B dash plus C dash plus D dash or A dash? Do you notice that neither one is bigger? They are equal because the length of PQ is 2A dash and it is also equal to 2B dash plus 2C dash plus 2D dash. It follows that A dash is equal to B dash plus C dash plus D dash. Hence, the two paths have equal length. Page number 129. Exercise set 6.1. Unless stated otherwise, use the approximation 22/7 for pi. Question number 1. The perimeter of a circle is 44 centimeters. What is its radius? Question number 2. Calculate correct to 3 significant figures. The circumference of a circle with first part radius 7 centimeters, second part radius 10 centimeters, third part radius 12 centimeters. Question number 3. Calculate the length of the arc of a circle if first part the radius is 3.5 centimeters and the angle at the center is 60 degrees, and second part the radius is 6.3 meters and angle at the center is 120 degrees. Question number 4. Find the perimeter of a sector, that is the curved portion as well as the two straight portions of a circle of radius 14 centimeters and sector angle 75 degrees. Question number 5. Find the perimeters of the following shapes, taking the arcs to be quarter or half or 3/4 of a circle as approximate. In figure 6.14, in figure 6.141 to 6.149, you are provided with 9 different figures to calculate the perimeters of the shapes provided. Page number 130. Question number 6. If the diameter of a car tire is 56 centimeters, then first part, how far does the car need to travel for the tire to complete one revolution? Second part, how many revolutions does the tire make if the car travels 10 kilometers? Question number 7. Find the total perimeter of all the petals in each of the given flowers. First one, figure 6.15a. The centers of the arcs are the midpoints of the sides of a square. Here we have 4 petals inside a square of side length 14 centimeters. In the second picture, figure 6.15b, the centers of the arcs are the vertices of the hexagon. We have 6 petals inside the hexagon. The side of the hexagon measures 42 centimeters. Question number 8. The ratio of the perimeters of two circles is 5:4. What is the ratio of their radii? 6.6 area of a rectangle. From perimeter, we move to area, that is, to the amount of space occupied by a two-dimensional region in a plane. Measurement is always relative to something we call a unit. For area, the unit is a 1 into 1 square. Its area is taken to be 1 unit square, also written as 1 square unit. You know from grade 8 that the area of a rectangle with sides A units and B units is A into B square units. We are provided with figure 6.16, which reflects area of square and rectangle. In the first one, we have area of a square having side length as 1 unit to be 1 square units. In the next figure, we have a rectangle with side length 1 unit and breadth as B. So area is equal to B square units. In the next picture, we have a square of side length A units. So area is equal to A square square units. In the next picture, we have a rectangle of length B units and breadth A units. Area equal to A into B square units. 6.7 Area of a parallelogram. You also know from grade 8 the formula for the area of a parallelogram. Page number 131. Figure 6.17 explaining area of parallelogram. Here A dash B dash C dash D dash is a copy of A B C D. In the first picture we have parallelogram A B C D, and in the next picture we have A dash B dash C dash D dash as a parallelogram and E B dash C dash F as a rectangle of height H and base as B. Figure 6.17 explains how to transform a parallelogram ABCD into a rectangle EB dash C dash F. At right, here parallelogram A dash B dash C dash D dash is a copy of ABCD with the same base B and same height H. Though the two shapes are different, their areas are the same. So, the area of the parallelogram is equal to base into height, that is equal to B into H. Think and reflect. What happens if the parallelogram is thin, as given in figure 6.18, and the foot of the perpendicular from C to AD does not lie on side AD? The construction then does not seem to work. How do we fix this gap? Here in figure 6.18, we have parallelogram ABCD with the perpendicular lying outside the parallelogram. Here is a hint on how the problem of the thin parallelogram can be solved. Select a point D dash on DA, close to D, and a point A dash on DA extended with A dash A equal to D dash D, as given in figure 6.19. Then A dash B C D dash is a parallelogram, and since triangle CDD dash is congruent to triangle BAA dash, its area is the same as that of ABCD. Now repeat this step as many times as needed. In figure, we have 6.19, a thin parallelogram which reflects ABCD as the thin parallelogram, and we have another thin parallelogram with sides A dash, B, C, D dash with congruent triangles. as A dash B A and D dash C D green in color. Think and reflect. The area of a rectangle can be found when we know the lengths of its sides. Is the same true for a parallelogram? That is, can we find the area of a parallelogram when we know the lengths of its sides? Why or why not? Page number 132. Hint provided is what happens to the area of a parallelogram if we decrease or increase the angle between the adjacent sides while keeping the lengths fixed. 6.8 Area of a triangle. Next, we work out a formula for the area of a triangle. You have seen 6.8 Area of a triangle. Next, we work out a formula for the area of a triangle. You have learnt the formula in grade 8, but we will go over the idea again briefly. One way to proceed is to first consider the case of a right angle triangle and then other triangles. In both cases, we enclose the triangle in a rectangle, then we use the formula for area of a rectangle. As given in figure 6.20a, notice that FG is equal to FJ plus JG, and so B is equal to B1 plus B2. We find as a result that the area of a triangle with base B units and height H units is half the area of the rectangle with base B units and height H units. That is, the area is equal to 1/2 B into H square units. You may wonder, like earlier, is there a gap in our argument? What would we do if angle EFG is obtuse and the triangle was shaped like triangle EFG in figure 6.20b? Please work out the answer to this question. Here we have in figure 6.20a area of a triangle explained with the help of 3 figures. In the first one, we have rectangle ABCD in which AC diagonal is drawn and AB represents the height H and BC represents the base B. In the next picture, we have FGIH, a rectangle, and we have a triangle with base FG. The triangle is EFG with height EJ and base as B1, FJ is base B1 and JG is base B2. In the next picture, figure 6.20b, we have a triangle EFG given here. A nicer way of working out the formula for the area of a triangle is by observing that 2 congruent copies of a triangle can be fitted together to make a parallelogram. Here we have 2 pictures. In first picture, in figure 6.21a, we have 2 congruent triangles, namely ABC and triangle A dash, B dash, C dash. In the next picture, that is figure 6.21b, we have a parallelogram ABCD in which diagonal AC is represented with the help of a dotted line. In figure 6.21a, triangles ABC and A dash, B dash, C dash are congruent. They fit together as in figure 6.21b to make a parallelogram. Page number 133. Do you notice why the two triangles fit together to make a parallelogram? If you study the angles in the figure, example, angle B dash, C dash, A dash and angle BCA, you will observe why this is so, keeping in mind the criterion by which we check whether two lines are parallel. We already know area of a parallelogram is base into height, that is equal to B into H. So, the formula for the area of a triangle is 1 upon 2 multiplied by base into height, that is equal to 1 upon 2 into B into H. A property of the median of a triangle. From the given formula, we reach a simple but beautiful conclusion about any of the medians of a triangle. A median is the line segment joining a vertex of the triangle to the midpoint of the opposite side. In figure 6.22, we have a triangle ABC with AD as median, D is marked as midpoint of BC and BD is equal to DC is represented here. Base BC is equal to 2A units and the perpendicular on BC is represented as height H with respect to A and BC. Consider triangle ABD and triangle ACD. Their bases are equal. BD is equal to DC and they have equal height H. Using the formula for the area of a triangle, we notice that they have equal area AH upon 2 square units. We state this as a theorem. Theorem is, a median of a triangle divides it into two triangles with equal area. Does this come as a surprise? It should. After all, triangle ABD and triangle ACD are in general differently shaped, that is, not congruent to each other. But we have just proved that they have the same area. Think and reflect. Since triangle ABD and triangle ACD have equal area, you may wonder, can we divide triangle ABD using straight cuts into two or more pieces that we can then rearrange to exactly cover triangle ACD? What do you think? Is it possible? We shall spoil the surprise by revealing that it is possible. But we will not tell you the least number of pieces required. Try to find the answer. Page number 134. Think and reflect. Suppose we are given two polygons, P and Q, with equal area. Will it always be possible to divide one of them using straight cuts into two or more pieces and then rearrange the pieces to exactly cover the other polygon? Try this out for familiar shapes. Example, first one, a square and non-square rectangle with equal area. Second one, two triangles with different shapes but equal area. Third one, a triangle and a square with equal area. Formulate a conjecture of your own about this. Think of various rectangles with perimeter 40 units. The sides do not have to be integers. First question, how many such rectangles are there? Question number 2. Among them, is there one whose area is the largest? What are its dimensions? Question number 3. Among all these rectangles, is there one whose area is the smallest? What are its dimensions? Do either of these answers come as a surprise to you? 6.8.1 Heron's Formula. You already know a formula for the area of a triangle, half base times height. Are there other formulas for the area of a triangle? There are several. For now, we mention Heron's Formula, discovered by the Greek mathematician and inventor Heron. He taught at the museum in Alexandria, a city in ancient Egypt located on the banks of the Nile. The formula states that if triangle ABC has side lengths BC is equal to A, CA is equal to B and AB is equal to C, then its area can be found as follows. First, we compute the semi-perimeter S, which is half the perimeter. S is equal to 1 upon 2 within brackets A plus B plus C. Then the area triangle ABC is given by square root of S into S minus A into S minus B into S minus C. I am sure you will find the formula extremely surprising and strange looking. Let us test it against some known cases. Example 3. An equilateral triangle with side A units. Page number 135. All three sides have length A. So, the semi-perimeter is S is equal to half of within brackets A plus A plus A. That is equal to 3 upon 2 into A units. Heron's formula now yields area of triangle is equal to square root of 3 upon 2 into A multiplied by 1 upon 2A multiplied by 1 upon 2A again multiplied by 1 upon 2A. That is equal to square root of 3 upon 4 A square units. Let us check this against the half base times height formula. Let h units be the height of the triangle. Then, by the Bodhain-Pythagoras theorem, a square minus h square is equal to a square upon 4. Therefore, h square is equal to 3a square upon 4. Therefore, h is equal to square root 3 upon 2 into a. So, the area is 1 upon 2 into square root 3 upon 2 into a. That is equal to square root 3 upon 4 into a square units. Same formula. Here we are provided with a figure 6.23 in which we find triangle ABC with D as the median and AD is the perpendicular whose height is h, and each side of the triangle is given as A. BD is marked as A upon 2 as D is the midpoint and DC also is represented as A upon 2. Notice the symbol 3 dots. This symbol is used regularly by mathematicians. It means and is read as therefore. Example 4. An isosceles triangle with equal sides A units and base 2B units. The semi-perimeter is S is equal to 1 upon 2 within brackets A plus 2B is equal to A plus B units. Heron's formula now yields area of the triangle is equal to square root of A plus B within brackets A plus B minus A within brackets A plus B minus A within brackets into A plus B minus 2B. That is equal to B into square root of a square minus b square square units. Let us check this against the half base times height formula. Let h units be the height of the triangle. Then, by the Bodheim-Pythagoras theorem, a square minus h square is equal to b square. Therefore, h square is equal to a square minus b square. H is equal to square root of a square minus b square. So, the area is 1 upon 2 into square root of a square minus b square into 2b. That is equal to b into square root of a square minus b square square units. The same as earlier. Here we are provided with figure 6.24 in which we find triangle ABC and AD is the perpendicular bisector of BC. So AB and AC both are equal to A and BD is equal to B and DC also is equal to B. Page number 136. Example 5. A triangle with sides 3 units, 4 units and 5 units. The semi-perimeter is S is equal to 1 upon 2 within brackets 3 plus 4 plus 5. That is equal to 6 units. Heron's formula now yields area of triangle is equal to square root of 6 into within bracket 6 minus 3 into within bracket 6 minus 4 into within bracket 6 minus 5. That is equal to square root of 6 into 3 into 2. That is equal to 6 square units. Let us check this against the half base times height formula as given in figure 6.25. Note that 3 square plus 4 square is equal to 5 square. Therefore, by the converse of the Bodheim-Pythagoras hypotenuse theorem, triangle ABC is right angle at B. So, base is equal to 3 units, height is equal to 4 units. So, the area is 1 upon 2 into base into height. That is equal to 1 upon 2 into 3 into 4. That is equal to 6 square units. The same as earlier. Here we have another picture in figure 6.25 in which we can find triangle ABC which is right angled and we have BC is equal to 3, AB is equal to 4 and AC is equal to 5 units. We get the correct result in each case. You may wonder how Heron's formula is proved. There are many proofs known. One of them uses the Bodheim-Pythagoras theorem and repeated use of the difference of two squares formula, that is a square minus b square is equal to a minus b into a plus b. We will study some of these proofs in grade 10. There are two other such formulas for the area of a triangle. Both have a connection with circles, as given in figure 6.26. Given any triangle ABC, there is exactly one circle that passes through its 3 vertices. This is called the circumcircle of triangle ABC. There is also exactly one circle that fits tightly in the triangle, touching its 3 sides. This is called the inner circle of triangle ABC. Let the sides of triangle ABC be A, B and C. Let the radius of the circumcircle be R. Let the radius of the inner circle be small r. Then we have the following two formulas for the area. Area of triangle ABC is equal to A into B into C upon 4 into R. Area of triangle ABC is equal to small r multiplied by A plus B plus C within brackets upon 2. We also have a figure on this page as figure 6.26, where we find a triangle ABC having a circumcircle with radius capital R. We also have a small inner circle inside the triangle ABC as incircle with radius small r. This incircle touches the sides of the triangle at small a, small b and small c respectively along the sides BC, CA and AB. Page number 137. Both formulas have a beautiful symmetry about them. The proof of the second formula requires a result that you will study in grade 10. Brahmagupta's formula for the area of a cyclic four-gone. We have learned how to find the area of a triangle given the lengths of its three sides. The natural question then is, how can we find the area of a four-gone given the lengths of its four sides? Earlier, we asked, can we find the area of a parallelogram if we know only the lengths of its sides? The answer is no. In the same way, we ask, can we find area of a four-gone if we only know the length of its sides? The answer given here reveals the answer to this question. The problem, as given in figure 6.27, is about a four-gone whose sides are known to be 3, 3, 3, 3. It is a rhombus. As you can find, the areas of the three figures are different. We drew the figures using GeoGebra and found the areas using the area tool. Please try this exercise yourself or by using four rods joined together at their ends. Here in figure 6.27, we have the areas of a four-gone cannot be found only from the lengths of its sides. We have three pictures of parallelograms, that is four-gone, A, B, C, D with area is equal to 9 and A, B, C, D rhombus with area equal to 8.01. Here we have again a four-gone A, B, C, D with area 5.41. So, we cannot find the area of a four-gone only from the length of its four sides. We need more information. This could be one angle of the four-gone or the length of one diagonal or the angle at which the diagonals cut each other, etc. Or it could be a key geometric property of the figure. One such property is that the four-gone is a cyclic four-gone. In 628 CE, Brahmagupta in 598 to 668 CE discovered a wonderful formula for the area of a cyclic four-gone. Page number 138. The formula states that if the sides of the cyclic four-gone have lengths A, B, C, D and the semi-perimeter S is equal to 1 upon 2 within brackets A plus B plus C plus D, then area of a four-gone is equal to square root of within brackets S minus A multiplied by within brackets S minus B multiplied by within brackets S minus C multiplied by within brackets S minus D. It is an amazing and beautiful formula. Does it not remind us of Heron's formula for the area of a triangle? Here we are provided with a figure 6.28. We can find a cyclic four-gone here. The four-gone ABCD has all the 4 points lying on the circle. and the side AB is represented with small a, BC is represented by small b, and CD is represented with small c, and AD is represented with small d letter. We can verify that the formula works out correctly in various special cases. Example 6. Verify Brahmagupta's formula for the case of a rectangle. All rectangles are cyclic, so Brahmagupta's formula should apply. Let the sides of the rectangle be A and B. Then S is equal to 1 upon 2 within brackets 2A plus 2B, that is equal to A plus B. So the formula yields area is equal to square root of A plus B minus A within brackets multiplied by A plus B minus B within brackets multiplied by A plus B minus A within brackets multiplied by A plus B minus B within brackets, that is equal to square root of AB into AB, that is equal to AB, which is correct. Please check out the formula against other special cases. Example 7. Verify Brahmagupta's formula for the case of an isosceles trapezium. All isosceles trapezia are cyclic. Hence, the formula should apply. The perimeter is 2A plus 2B plus 2C. So, S is equal to A plus B plus C. Hence, the area is given by the formula should be square root of S minus 2A within brackets multiplied by S minus 2B within brackets multiplied by S minus C within brackets multiplied by S minus C. Since S minus 2A is equal to C plus B minus A, S minus 2B is equal to C plus A minus 2B, S minus C is equal to A plus B. The above formula simplifies to A plus B within brackets square root of C plus B minus A within brackets multiplied by C plus A minus B within brackets, that is equal to A plus B within brackets into square root of C square minus B minus A whole square. We also have a figure 6.29 where we can find isosceles trapezium ABCD, where AD and BC are equal to C and AB and DC are of each length 2A and 2B respectively, and the height between the parallel sides AB and DC is represented with H alphabet. Page number 139. If we imagine a perpendicular dropped from B to the base CD, its length, recall the Bodhaina-Pythagoras theorem, is square root of C square minus within brackets B minus A whole square. Hence, the area is A plus B within brackets into H. We get exactly the same formula if we recall that the area of an isosceles trapezium is half the sum of the parallel sides times the distance between the parallel sides. Special cases and generalization in mathematics. The notion of a special case occurs often in higher mathematics. A special case results from a general result whenever we apply some extra condition. We list a few such examples. The general result is also called a generalization of the special case. The process of generalization is an extremely important part of mathematics. Example, a square is a special case of a rectangle. So, the formula for the area of a square A is equal to A square is a special case of the formula for the area of the rectangle A is equal to A into B, obtained by putting B is equal to A. Similarly, the formula for the perimeter of a square is a special case of the formula for the perimeter of a rectangle. Example, an isosceles right angle triangle is a special case of a right angle triangle. So, from any theorem about all right angle triangles, we can extract a special case that applies to isosceles right angle triangles. Take a right angle triangle ABC with angle C is equal to 90 degrees. Then we have A square plus B square is equal to C square. This is the Bodhaina-Pythagoras theorem. Let us take a special case of this with A is equal to B. This corresponds to the triangle being isosceles. We get A square plus B square is equal to C square. That is, C square is equal to 2A square, and so C is equal to A square root 2. The general theorem A square plus B square is equal to C square has reduced to this special case. C is equal to A into square root 2 for isosceles right angle triangles with A is equal to B. Here is another example. Compare the following identities from algebra. A plus B whole square is equal to A square plus B square plus 2AB. A plus B plus C whole square is equal to A square plus B square plus C square plus 2AB plus 2BC plus 2CA. Can you notice that the first identity is a special case of the second one? Put C is equal to 0 in the second identity, and the second identity is a generalization of the first one. You will meet many examples of special cases and generalization in later years. Page number 140. Brahmagupta's formula generalizes Heron's formula. The similarity in appearance between Heron's formula and Brahmagupta's formula is not an accident. How? Brahmagupta's formula generalizes Heron's formula. That is, we can think of Heron's formula as a special case of Brahmagupta's formula. A triangle with sides A, B, C can be regarded as a special case of a foregone ABCD, whose fourth side D has zero length, that is D is equal to 0. So, we have AB is equal to A, BC is equal to B, CD is equal to C, which means in effect that vertices A and D coincide. If the vertices represent planets, then this would be a case of two planets colliding with each other and forming a single large planet. This actually happened in the early history of the solar system. Since any triangle is cyclic, given any 3 points, not in a straight line, we can draw a circle through them. This foregone is cyclic too. So, Brahmagupta's formula must apply to this foregone. Let us notice what emerges from this. We first compute the semi-perimeter of the foregone, keeping in mind that D is equal to 0. S is equal to 1 upon 2 within brackets A plus B plus C plus 0 is equal to 1 upon 2 multiplied by A plus B plus C. We find that S is the same as the semi-perimeter of the given triangle. Now we apply Brahmagupta's formula. Area of triangle is equal to square root of S minus A within brackets into S minus B within brackets into S minus C within brackets into S minus D. That is equal to square root of S into S minus A multiplied by S minus B multiplied by S minus C within brackets, since D is equal to 0. This is Heron's formula. Brahmagupta's formula may thus be viewed as a generalization of Heron's formula. 6.9. Squaring a rectangle. In ancient times, to square a given shape means to construct a square equal in area to that shape. The shape could be a rectangle or a triangle or a circle. Here we explain how the ancient Indian mathematician Bodhaina squared a rectangle. The construction from his Sulba Sutra 800 BCE explains how to square a rectangle with sides A units and B units where A is greater than B. Page number 141. This means that we must construct a square with area AB square units. Here is a slightly simplified form of Bodhain's construction. Figure 6.30. Given rectangle ABCD with AD is equal to A, AB is equal to B, where A is greater than B. Locate E on AD so that AE is equal to AB. Locate the midpoint F of ED. Draw square AFGH with side AF and vertex H on AB produced. Draw arc AG with center H. Let arc AG cut side BC at K. Draw a line through K parallel to AH. Let it cut GH at P. Draw square HPQS with HP as side. Then square HPQS has the same area as rectangle ABCD. We have this explained in figure 6.30. We have rectangle ABCD with AD is equal to A and AB is equal to B. We have a rectangle ABCD which is pink in color, and we also have a rectangle AFGH represented on this, and we also have a square SQPH where B and K are midpoints of HS and PQ respectively. H and K are joined with dotted lines. We also have an arc with A, K and G inside the rectangle AFGH. Try to work out why this method works. You will find that it is a geometrical translation of the formula A plus B upon 2 whole square minus A minus B upon 2 whole square is equal to AB. Why does this method work? Refer to figure 6.30. From AE is equal to B, we get AF is equal to AE plus AD upon 2, that is equal to A plus B upon 2. Hence, HG is equal to A plus B upon 2, that is equal to HK, as HK is a radius of the circle. Next, BH is equal to AH minus AB, that is equal to AF minus AB, that is equal to A plus B upon 2 minus B, that is equal to A minus B upon 2. Now consider the right angle triangle HKP. Using the Bodhain-Pythagoras theorem, we get HP square is equal to HK square minus BH square, that is equal to A plus B upon 2 whole square minus A minus B upon 2 whole square, that is equal to A square plus 2AB plus B square upon 4 minus A square minus 2AB plus B square upon 4, that is equal to AB upon 2 plus AB upon 2, that is equal to AB. Therefore, square HPQS has the same area as rectangle ABCD. Page number 142. Think and reflect. What procedure would you use to square a given triangle? Here, the task is to construct a square whose area is equal to the area of some given triangle. Think carefully. How would you proceed? Exercise set 6.2. Question number 1. Find the area of the triangle ADE in figure 6.31. In figure 6.31, we have rectangle ABCD in which we have a triangle with base AD and triangle is AED with height 10 centimeters, which is the length of the rectangle also. DC is equal to 10 centimeters and other side of rectangle BC is 8 centimeters. Question number 2. The parallel sides of a trapezium are 40 centimeters and 20 centimeters. If its non-parallel sides are both equal, each being 26 centimeters, find the area of the trapezium. Question number 3. Find the area of a triangle given that its sides are 8 centimeters and 11 centimeters long and its perimeter is 32 centimeters. Question number 4. The sides of a triangular plot are in the ratio 3:5:7. Its perimeter is 300 meters. Find its area. Question number 5. One diagonal of a rhombus is twice as long as the other diagonal. If the rhombus has area 128 centimeter square, find the length of the shorter diagonal. Question number 6. ABCD is a parallelogram. P and Q are any two points on side AB. What can you say about the ratio area triangle PCD is to area of triangle QCD? Question number 7. O is any point on the diagonal PR of a parallelogram PQRS. Prove that the areas of triangles PSO and PQO are equal. Question number 8. If the midpoints of the sides of a fourgon, also known as a quadrilateral, but we prefer to call it a fourgon, are joined in order, prove that the area of the parallelogram thus formed will be half of the area of the given fourgon. Page number 143. You may wonder whether the fourgon thus formed is always a parallelogram, and if so, why? These questions will be tackled and answered in the chapter on quadrilaterals. Question number 9. In triangle ABC, the midpoint of BC is D. In figure 6.32, median AD is drawn. P is any point on AD. Explain that area of triangle ABP is equal to area of triangle ACP. We have figure 6.32 in which we find a triangle ABC and D is a midpoint of BC. We have AD is median joined here, and we also can find a triangle PBC with bases BD and DC, which are represented to be equal. We have another picture here in figure 6.33. We have ABCD as a square and we have P as any point inside the square, thus forming four triangles, namely APB, BPC, CPD and APD. Question number 10. Given a square ABCD, let P be a point within it. Join PA, PB, PC, PD as given in figure 6.33. What is the ratio of the areas of the red region, triangle PAB and triangle PCD, and the green regions of triangle PBC and triangle PDA? Question number 11. In triangle ABC, D is the midpoint of AB, P is any point on BC, and Q is a point on AB, such that CQ is parallel to PD. PQ is joined as given in figure 6.34. Prove that area of triangle BPQ is equal to half the area of triangle ABC. In figure 6.34, we have triangle ABC with points P on BC and points D and Q on AB. PQ is joined and DP is joined by dotted lines, and QC is also joined with dotted lines. We have DP parallel to QC represented in the figure. 6.10. Area of a circle. A circle is an extremely basic shape. It is easy to draw if we have a rope and a peg to which the rope can be tied. Human beings have used the circular shape in their settlements, buildings, and tools for thousands of years. Page number 144. Think and reflect. Why were human beings so fond of using circular shapes? Was this only for practical reasons, or could there have been other reasons too? What kinds of uses have human beings found for the circular shape? Early on, human beings faced the challenge of finding the area A enclosed by a circle. They may have needed, for example, to work out how much grain can be kept in a cylindrical tower, which has a circular cross-section, or how much area is occupied by a circular garden or a circular building. They needed such data for planning out their cities, for tax purposes, etc. Early societies understood very well that the area A must be proportional to the square of the circumference C. Let's find why this is so. Suppose we are given a square. Let its sides be A. It has perimeter P is equal to 4 into A, and area A is equal to A square. So the ratio P square is to A is equal to 4A square is to A square. That is equal to 16A square is to A square. That is equal to 16 is to 1. So the ratio P square is to A is 16 is to 1. For all squares, the ratio does not depend on the size of the square. It is the same for all squares. Consider an equilateral triangle with side A. Its perimeter is P is equal to 3A and its area is A is equal to square root 3 upon 4 into A square. So, P square is to A is equal to 3A whole square is to root 3 upon 4 A square. That is equal to 9A square is to root 3 upon 4 into A square. That is equal to 36 is to root 3. So, the ratio P square is to A is 36 is to square root 3. For all equilateral triangles, the ratio does not depend on the size of the equilateral triangle. It is the same for all equilateral triangles. Similarly, for various shapes, as we change the scale, the ratio P square is to A stays fixed. The value of the ratio depends only on the shape, not on its scale. Such reasoning suggests that for a circle too, if C is equal to circumference and A is equal to area, the ratio C square is to A must be some fixed constant. But what is this constant? Well, before 1500 BCE, the Babylonians had found through actual measurement that the constant is close to 12. That is, C square is to A is approximately equal to 12 is to 1. So, their formula for the area of the circle was A is equal to C square upon 12. Around 1500 BCE, the ancient Egyptians came up with another such formula which resembles the one described here but is much more accurate. A is approximately equal to 8d upon 9 whole square, where d is the diameter of the circle. Page number 145. Since d is equal to 2r, this may also be written as A approximately equal to 64 upon 81 multiplied by 4r square. That is, A is approximately equal to 256 upon 81 within brackets multiplied by r square. Amazingly, the same formula appears in the Bodhayan Sulbha Sutra 800 BCE via a geometric method for constructing a square with approximately the same area as a circle, the familiar formula in use today. The ancient Greeks also knew that A upon r square is some constant, but did not know what that constant was. Two different civilizations approximated it to be 256 upon 81. Finally, in c. 250 BCE, Archimedes explained that the constant is exactly pi, that is, the same constant that occurs in the formula for perimeter of a circle. So, A is equal to pi r square. He expressed the formula this way: the area of a circle is equal to the area of a right angle triangle with sides equal to the radius and the circumference of the circle. That is, area of the circle is equal to 1 upon 2 into circumference into radius. That is equal to 1 upon 2 into 2 pi r into r, that is equal to pi r square. The proof given by Archimedes is very clever. It is based on a property shared by all regular polygons. The area enclosed by a regular polygon is equal to half the perimeter multiplied by the radius of the circle that fits tightly within the polygon, as given in figure 6.36. The proof of this formula is an extension of the proof of the formula of the area of a triangle in terms of the radius of its incircle. Here we have figure 6.36, where we can find area of a regular polygon is equal to half multiplied by perimeter of the polygon into radius. We have three different figures. In first figure we find a triangle. Inside this we have a circle of radius r, and the center of the circle is O, and radius is also expressed here in the figure. In the second picture we have a pentagon, that is 5 sides, and inside which we find a circle with center O and radius r. Here also circle touches all the sides of the pentagon. In the next picture we have a heptagon having 7 sides. We have a circle with center O and radius r, which touches all the sides of the heptagon. Page number 146. Archimedes did a thought experiment. He asked himself, what happens if the number of sides of the regular polygon gets larger and larger? Working out the details, he arrived at the result A is equal to pi r square. Here, perhaps, is the most visual and easy to understand explanation for why the area of a circle of radius r has area pi r square. This beautiful visual explanation for the area of the circle was first discovered by Nilakant Somayaji c. 1500 in his commentary on the Aryabhatiya. Here we are provided with a figure 6.37 in which we can find the slices can be rearranged to form a parallelogram-like structure. In figure A, we have a circle with different sectors of a circle in yellow and orange color, and these slices have been again arranged in the form of a parallelogram in figure B. As the slices become smaller and smaller, the arcs in figure become more and more closer to a line. This makes the figure more and more closer to a parallelogram with base is equal to half the circumference y within brackets, that is equal to pi r. Height is equal to radius, that is equal to r. This gives a way to argue that the area of the circle is equal to the area of a parallelogram. Area of the circle is equal to area of the parallelogram, that is equal to base into height, that is equal to pi r square. 6.10.1 Area of sector of a circle. A sector of a circle is the region bounded by an arc and the two radii containing the endpoints of the arc. The area within a sector of a circle may be found the same way that we found the length of a circular arc. Examine as given in the figure 6.39 and figure 6.40. Here we are provided with a figure 6.38 representing sector of a circle. We have RKB which subtends angle at O and degree theta degrees. Page number 147. By symmetry, we find that the area of semicircular disc is 180 degrees upon 360th, that is equal to 1 upon 2 of the area of the circle, that is 1 upon 2 pi r square. We would use the reflection symmetry of the circle to understand this result. Here in figure 6.39, we have area of semicircular disc. AB is the diameter of the circle given here. Half circle is painted pink and the other half is painted purple. Center of the circle is represented with O and radius is represented with R. By symmetry, we find that the area of a quarter circular disc is 90 upon 360th, that is equal to 1 upon 4 of the area of the circle, that is 1 upon 4 pi r square. We could also use the quarter turn symmetry of the circle to understand this result. In figure 6.40, we have area of a quarter circular disc. Here we have a circular disc in which we can find 4 different sectors, that is AOB, BOC, DOC and DOA, respectively in color pink, blue, purple and green. We could also use the quarter turn symmetry of the circle to understand this result. Examining this, we immediately obtain the desired formula for a general sector. Formula for the area of a sector of a disc in terms of the angle it subtends at the center of the circle. If the arc is AB and it subtends an angle of theta degrees at the center O of the circle as given in the figure 6.38, then the area of the sector is pi r square multiplied by theta degrees upon 360 degrees. Note how we have used the rotational symmetry of a circle in deducing these formulas. Related to a sector, there is a part of the circular region called a segment. A segment of a circle is the region bounded by an arc of the circle and the chord joining the endpoints of the arc. Page number 148. Exercise set 6.3. Unless stated otherwise, use the approximation 22/7 for pi. Question number 1. Find the area of a sector of a circle with radius 7 cm if the angle of the sector is 60 degrees. Question number 2. Find the area of a quadrant of a circle whose circumference is 44 cm. Question number 3. The length of the minute hand of a clock is 7 cm. Find the area swept by the minute hand in 10 minutes. Question number 4. A chord of a circle of radius 10 cm subtends 90 degrees at the center. Find the area of the corresponding first part minor sector that subtends 90 degrees at the center, and second one, major sector that subtends 270 degrees at the center. Use pi approximately equal to 3.14. Question number 5. A chord of a circle of radius 15 cm subtends an angle of 60 degrees at the center of the circle. Find the areas of the corresponding minor and major segments of the circle. Use pi approximately equal to 3.14 and square root 3 approximately equal to 1.73. Question number 6. A car has two wipers which do not overlap. Each wiper has a blade of length 28 centimeters and sweeps through an angle of 120 degrees. Find the total area cleaned at each sweep of the blades. Question number 7. A chord of a circle of radius r subtends an angle of 60 degrees at the center of the circle. Explain that the area of the corresponding minor segment of the circle is equal to pi r square multiplied by 1/6 minus square root 3/4 within brackets. Question number 8. An equilateral triangle is inscribed in a circle of radius r. Show that the ratio of the area of the triangle to the area of the circle is equal to 3/√3 divided by 4 pi, which is approximately equal to 0.413. Question number 9. A square is inscribed in a circle of radius r. Show that the ratio of the area of the square to the area of the circle is equal to 2/pi, which is approximately equal to 0.637. Question number 10. A hexagon is inscribed in a circle of radius r. Show that the ratio of the area of the hexagon to the area of the circle is equal to 3/√3/2 pi is approximately equal to 0.827. Can you find why the answer is exactly twice the answer to question 8? Page number 149. In the problems given here, unless stated otherwise, use the approximation 22/7 for pi. Question number 1. Identities in algebra can sometimes be represented as area relationships. For example, the figure given here corresponds to the identity a plus b whole square is equal to a square plus 2ab plus b square. Do you find how? We have figure 6.41 with area model of an identity. We have square of side a plus b, which can be split in two squares of area a square and b square, and also two rectangles having area AB. Draw figures corresponding to the identities a plus b multiplied by a minus b is equal to a square minus b square, and a plus b plus c whole square is equal to a square plus b square plus c square plus 2ab plus 2bc plus 2ca. Question number 2. An isosceles triangle has perimeter 40 centimeters. The equal sides are 15 centimeter each. Find the area of the triangle. Question number 3. An isosceles triangle has base 10 centimeters and its area is 60 centimeters square. What are the lengths of the equal sides? Question number 4. The area of a right angle triangle is 54 square centimeters. One of its leg has length 12 centimeters. Find its perimeter. Question number 5. The sides of a triangle are in the ratio 2:3:4 and its perimeter is 45 centimeters. Find its area. Question number 6. The sides of a triangle have lengths 7 centimeters, 24 centimeters, 25 centimeters. Find the area of the triangle in two different ways. Question number 7. If the wheel of a bicycle has a diameter of 60 centimeters, find how far a cyclist will have travelled after the wheel has rotated 100 times. Page number 150. Question number 8. Find the area of a quadrant of a circle whose circumference is 66 centimeters. Question number 9. The wheel of a car has an outer radius of 28 centimeters. Calculate how far the car travels after one complete turn of the wheel and how many times the wheel turns during a journey of 1 kilometer. Question number 10. Two rectangles have the same area and the same perimeter. Does this mean that they are congruent to each other? Question number 11. You know that the area of a parallelogram is base into height. Using this and the figure, explain that the area of a trapezium is half the sum of the parallel sides multiplied by height. That is 1/2 within brackets a plus b into h. Here we have figure 6.42 with a trapezium having sides a and b and height h. Question number 12. By dividing a trapezium into two triangles, explain that its area is half the sum of the parallel sides multiplied by the height. The same formulas as the one given here. Question number 13. Explain how we can use two identical copies of a trapezium to make a parallelogram. How will this give us the formula for the area of a trapezium? Question number 14. Explain that the area of a kite is half the product of its diagonals. Explain this in the first part using algebra and second part using geometry. Question number 15. 3 problems about fitting congruent shapes together. First part, rectangle ABCD has sides A, B and rectangle PQRS has sides 2A, 2B. Explain that PQRS has 4 times the area of ABCD. Does this mean that 4 copies of rectangle ABCD will fit into rectangle PQRS? Check and find. Page number 151. Second part. Triangle ABC has sides A, B, C and triangle PQR has sides 2A, 2B, 2C. Explain that triangle PQR has 4 times the area of triangle ABC. Does this mean that 4 copies of triangle ABC will fit into triangle PQR? Check and find. Third one. Triangle ABC has sides ABC and triangle PQR has sides 3A, 3B, 3C. Explain that triangle PQR has 9 times the area of triangle ABC. Does this mean that 9 copies of triangle ABC will fit into triangle PQR? Check and find. Question number 16. Here we are provided with a picture in which we find figure 6.43. What fraction of the triangle is shaded? We have a triangle in which we have one side to be divided into 2 equal parts and the other side of the triangle is divided into 3 equal parts, and the middle portion is shaded in purple color. In figure 6.44, what fraction of the square is shaded? Here we have a square and the midpoints of the sides of the square are used to draw the parallel lines, and the point of intersections are forming a square here. And the question is figure 6.44. What fraction of the square is shaded? Question number 17. Figure 6.45. What fraction of the rectangle is covered by the circles? Here we have a rectangle in which we find 3 circles placed adjacent to each other. We are supposed to find the fraction of the rectangle which is covered by the circles. In figure 6.46, what fraction of the rectangle is covered by circles? In this picture, we have a rectangle with 4 circles placed next to each other. Question number 18. Use this to make a conjecture about the area occupied by circles fitted into a rectangle in a manner given here. Test your conjecture for particular cases. 10 circles, 20 circles, 50 circles, then prove your conjecture. Question number 19. The figure given here has 9 identical rectangles fitted together to make a large rectangle whose area is 72 cm square. Find the perimeter of each small rectangle. We have in figure 6.47 9 identical rectangles stacked together one above the other. Page number 152. Question number 20. We have figure 6.48 in which we find lines from a vertex to the points of trisection of the opposite side in triangle given here. Explain that the areas of the shaded blue triangle and the shaded red triangle are equal. Find a way of cutting up the blue triangle into some number of pieces and arranging the pieces to cover the red triangle. Question number 21. In figure 6.49, a quarter circle and two semicircles are represented in the figure. The figure explains a quarter circle in a square. Its center is at one vertex and it passes through two adjacent vertices. There are two semicircles on two adjacent sides as diameters. They create the shaded regions A and B. Explain that A and B have equal area. Question number 22. In figure 6.50, four semicircles have been drawn within the given square whose side is 2 units. The centers of these semicircles are the midpoints of the sides. They create a 4-petaled flower as given in blue color. Find the perimeter and the area of this flower. We have a square of side 2 units and 4 petals inside the square. We are supposed to find out the perimeter and area of this flower in figure 6.50. Question number 23. In figure 6.51, we are given two concentric circles with a common center O. A chord BC of the larger circle is drawn touching the smaller circle at A. The length of BC is L. Explain that the area of the green region enclosed between the two circles is 1/4 pi L square. In figure 6.51, we have two concentric circles with center O and the area between the two concentric circles are shaded green and a line which touches the inner circle and outer circle is joined by line BC which is equal to L. Page number 153. Question number 24. In figure 6.52, semicircles have been drawn on all the sides of a right angle triangle as given here. Explain how area of portion A plus area of portion B is equal to area of portion C. We have figure 6.52 where we find that the right angle triangles have two semicircles on the sides of the smaller triangle, smaller length and the larger length. In figure 6.53, we have two congruent triangles with radius r. Here, two circles with center A and center B are intersecting each other with common area and the point of intersections are C and D. Question number 25. Figure 6.53 has two circles passing through each other's centers. Find the area of the region enclosed by the two circles in terms of the common radius r. Question number 26. In figure given here, we find three triangles within a rectangle. The areas of the triangles are A, B, C as marked. Explain that the area of the rectangle is 2 multiplied by A plus C within brackets multiplied by B plus C within brackets upon C. In figure 6.54, we are given three triangles within a rectangle and they have been marked as A, B and C. we are supposed to explain that the area of the rectangle is 2 times a plus c within brackets into b plus c within brackets upon c. Question number 27. In the figure, we find two shaded regions formed by a quarter circle, a semicircle and a triangle. In figure 6.55, we have a semicircle with diameter AC and center as O. There is a triangle AOB which is shaded, and D is the midpoint of the hypotenuse, which describes a semicircle on the hypotenuse with radius, and the outer portion is represented with E and the inner arc is represented by F. Explain that the areas of the two shaded regions are equal. Page number 154. Chapter Summary. Pi is the constant circumference to diameter ratio for all circles and is approximately equal to 22/7 or 3.14. Next, the circumference of a circle is given by C is equal to 2 pi r, where r is the radius of the circle. The arc length of a circle is given by L is equal to 2 pi r into theta degrees upon 360 degrees, where theta is the central angle. The area of a triangle is given by A is equal to 1/2 base times height. Heron's formula for the area of a triangle in terms of its sides A, B and C, area is equal to square root of S into S minus A within brackets multiplied by S minus B within brackets multiplied by S minus C within brackets, where S is equal to half of within brackets A plus B plus C. The area of a circle is given by A is equal to pi r square. Estimates for pi. Archimedes 3 whole 10/71 is less than pi less than 3 whole 1/7. Chongzai pi is approximately equal to 355/113. Aryabhatta pi is approximately equal to 3.1416. Madhava's extract formula pi is equal to 4 within brackets 1 minus 1/3 plus 1/5 minus 1/7 plus dash. Pi is an irrational number. The area of a sector of a circle is given by area is equal to pi r square into theta degrees upon 360 degrees, where theta is the central angle. Brahmagupta's formula for the area of a cyclic quadrilateral in terms of its sides A, B, C, D. Area is equal to square root of S minus A within brackets multiplied by S minus B within brackets multiplied by S minus C within brackets multiplied by S minus D, where S is equal to 1/2 within brackets A plus B plus C plus D. Chapter 6 ends here.
Ganit Manjari, Part 1. You were just listening to this audiobook. Textbook of Mathematics for Grade 9. Narration, Swarnlata Sharma. Sound recordist, Mohammad Faizan Khan. Assistance in production, Vineet Kumar Sharma. Directed and produced by Vimlesh Chaudhary. This audiobook is brought to you by CIET NCERT, New Delhi, India.